Hello and welcome to AP Computer Science with the Arupe Virtual Learning Institute. My name is John Maxwell. Today in this lesson we're going to cover searches and sorts of arrays. And you'll probably remember that we've covered searches in the last unit before Christmas, but here's a brief review. There's two searches you need to know for the computer science exam. You won't ever have to write any of the code for them, but you do have to have a pretty solid understanding of how they work. The first is linear search, and as the name implies, sometimes it's called sequential search. But that also implies that it's starting at the beginning and going all the way through the collection of values. And so we have a search element, which is key. We're searching for a value in the array. And we start at index 0 and go to the end with this for loop. And if we find that the key matches the value at the index, we return the index. If the for loop completes and we haven't found it or had a return, we return -1, signaling it was not found. The worst case scenario is that it goes all the way through the array and does not find the value, or it finds it, at the last position, pretty much the same. That's the worst case. The best case is that it finds it right away in the first position or in the first few. So it's not always bad, but it is always required when you have an unsorted array. Its companion search is called binary search, and it falls within a category of algorithms called divide and conquer. And again, it takes a key that you're looking for in the array of numbers, and it sets the low to 0 and the high to the numbers dot length -1, or in other words, the last index in the array. And it sets middle to low plus high divided by 2. So the first pass, we're going to examine the middle element. Let's call it the middle element. And if the middle element is not equal to the key and low on the first pass, will not be greater than high. But if it's not found, low will pass by high and be greater than. Then we're going to search. And so if the key is less than the middle, okay, what we want to do is bring the high down to the middle -1. And if the key is greater than the middle, we want to bring the key up to the middle -1 and recalculate the middle in both cases. Reset the middle. And so we'll continue through the loop, resetting the middle. And then when the loop stops, the number in the middle equal the key will return that middle indice. Else, if it gets all the way through the loop, we'll return -1, just like the previous algorithm. So, a little sample would be, I have numbers in a 100 element array from 1 to 100. What's your first guess? And the answer is 50, because you divide by 2. No, you're too low. So you bring the low up to 51, and the next guess is 75. And you're still too low, so you bring the low up to 76, and the next guess is 87, and so on and so forth. It's a very efficient search, but it takes advantage of the fact that the array is sorted. Okay, so the multiple choice question would be, in which case is linear search better than binary search? And the answer is when the element is in the first few indices of the array. And so this is a brief review of linear and binary search, and I'm just going to run a program where it shows, okay, and I'll run this and bring up the output and say, here we have a linear search, okay. 73 was found at index 6. And so here it is in this value of grades, okay? And then we sort it, and 73 is found at index 1 after the sort, okay? Using binary search over here. So how is that? Because we sorted it and we moved 73 to the second position at index 1 in the array after sorting, because it was the second least value in the grades array. So we're going to step into the sorts file to see how those work. Okay, this is the file that's given to you in the extra credit assignment, and it features selection sort here, and in comes a value numbers, and I copied over what those numbers were from the other file, 89, 95, 69, 80, 97, etc. The first thing you might notice is lines 11 and 14 are nested loops. And so what we're going to do is run our array through these and do the following. Let me explain how it works. Okay, real briefly. You know, the first time line 11 gets executed, okay, we are making an assumption that 89 is the lowest value. And what we're going to do is compare 89 versus every other value in the array. And if we find a value that's less than 89, such as 69 here, we're going to store it in a value called min. And then at the end, we'll swap those values down here using a traditional swap algorithm, which I hope you understand and can fathom. And after the first pass, the array becomes 69, 94, 89, 80, and the rest of the values. So again, what it does is it swaps 89 and 69 after finding that 69 was the minimum of the remaining values in the array. And so the second pass will look at 94 and it will compare it versus the now value at the next index, 89, 80, 97, and it'll find 73 as the minimum value and swap 94 and 73. So it does a lot of comparisons but fewer swaps. And the other video that I've assigned explains this much more graphically. So the purpose of this is really to show you what the code looks like, because the other video doesn't show you the code. We also have another sort mechanism called insertion sort. And if you look at it very carefully, it again consists of two loops. Now one's a while loop and one's a for loop, and the insertion sort works a bunch different than selection sort, making more comparisons and fewer comparisons but more swaps. Here's how it works. We're going to assume again that 89 is the sorted part of the array, which is at index 1, okay, 89 is the sorted part of the array. And then we're going to say, is 94 greater than 89? We'll make a comparison and we'll say no, that's it. So we've got a sorted array of 89 and 94. And then we'll examine the next element, 69, and we'll say, is that less than 94? And it'll be yes, and what we'll do is we'll swap 69 and 94, but we need to keep on going in this while loop here and ask, is 69 less than 89? And then we swap those two elements. So we swap the value at position, which is now set to position -1, and decrease the position. So we now have 69, 89, 94 in the sorted part of the array. And so the next number up is 80, and we say, is it less than 94? We'll swap it. Is it less than 89? We'll swap it. Is it less than 69? We found its place. Number, position equal key. So I've heard it said this way. You get a hand dealt to you, you pick up your cards, and then you start putting like the 2 of clubs, to the left of the 5 of clubs. You start like ordering them in some way, like, inserting the card where it belongs. And that is generally a description of it. And so we'll run it again. We'll say, look at selection sort, print it out twice, and I'll go back to sort grades and say, why don't we just insertion sort and run this program again. Now it produces the same result, and you would expect it. But is one better than the other? Well, not much, because they're both nested for loops. And if you follow the videos and not part of the curriculum, you'll know that's quadratic n squared as the predominant term in the mathematical analysis, which you don't have to know for this class. Stopped that quite a long time ago, but it used to be part of the class. Let me run this one here. Merge sort runner. No, not that one. Main. This is, by the way, the extra credit, so you might want to do a screen grab. Okay. Oh, let's make the array length 1,000. 1,000 random elements, that's quite a large array. And we'll run it 40 times, and we'll send the same array into selection and insertion sort, and we'll measure the time, the swaps, the comparisons, and here we go. Okay. Well, at first glance, it seems like insertion sort wins because the time is so much less. Well, we're talking milliseconds, by the way. I love computers, and they can sorting 1,000 element arrays in milliseconds, but great. But look at the swaps. The insertion sort has about 500,000 swaps and comparisons combined, 500,000. And selection sort has only 991 swaps, but it has almost 500,000 comparisons. So in terms of the number of operations, swaps and comparisons, they're about equal. So why is there a time difference? Well, you probably guessed it, and that is because when you randomly generate arrays, some arrays are going to be more in order than others. And whenever an array is in order, it does not have to make swaps or comparisons in the case of insertion sort. The element is already in its place, or it only needs to move a few spots in order to be in its place, so that it doesn't have to make as many comparisons, but it certainly makes more swaps. So that is the reason why insertion sort over time is slightly better than selection sort, but they're both ratchet in terms of being compared about something we'll be talking about later, which is merge sort. So here's a look at the selection sort algorithm. In order to send the same array in, I clone it. Okay, not something you're necessarily familiar with, although the assignment, and it works in large number, says use system time millis. Nanotime is a nice way of looking. Take a time measure before the sort and a time measure after the sort. You're going to have to choose large arrays, large sized arrays, in order to get the time to register. And then you keep track of the swaps and the comparisons. And I'm just going to give you a look at how I did that. Okay, and eventually, you'll average them based on the total comparisons, total time, and total swaps divided by 40. But let's take a look at the sorts a little bit. What it does is it returns an array, a two-element array of comparisons and swaps, and at various measures you put comparison and swap indicators in here where it occurs, and then you return the array of swaps and comparisons. So you can pause that and see. And the real beauty of it is that you'll have to repeat the code for insertion sort, but everybody gets the knowledge that insertion sort runs a little better in time because it takes advantage of the natural orderedness of a particular array. And so finally we go to merge sort, and the video explains it a bit better than I'm going to explain it here. Let me open up merge sort runner. And we'll just run it, and it shows that it works. The output of merge sort runner is pretty consistent, before or after. But let's look at merge sort and see how it does. Well, first of all, we have to understand that merge sort is a recursive algorithm. And notice we have two merge sort methods. We properly identified that is overloaded. And, over here we're calling the one with just the array. But here we're calling this one, which is the recursive merge sort. And here's, a broad-based summary. And we'll also mention that it creates an array called temp. And for each call of merge sort recursive down here, it creates a new temp array. So I'm going to return to that concept in a second, but I want to say, hey, looks like when I go left plus right minus left divided by 2, I'm doing a divide and conquer, aren't I? Well, that's really what's happened. And the idea is with all of the sorts is, let's assume that an array of one element is sorted. Duh. Of course, an array of one element is sorted, and so what we're going to do is we're going to divide it until we get an array of one element. So first, we sort the left half. Okay? And then we sort the right half. And then we merge them together. I've been dealing with a cold all week. I am so sorry for that. And I'm going to refer you to the video that is posted on the course site for a graphic application of that. But um, you will never have to write this algorithm. You will never have to write any of the sorts and search algorithms on your part two. You may look at them and a multiple choice question, and it'll be such that, like, you know, considering the following, and they won't even call it merge sort, so you'll have to identify, oh wow, this is a merge sort, what line needs to be changed in order to make it work as intended, so that you'll have some understanding of it. The only merge sort problem that I saw over the last 25 years that was interesting is they had a recursive solution for a binary search. And they asked you to identify the base case or something like that, or to fix it in some small way, so that, like, in general, this is something that is not tested, although it's part of the curriculum. And in any given year, you can have a surprise. So again, referring to the YouTube video posted on the website and looking at this code a bit and running it, and hopefully you'll get a better sense of how it works. This has been a discussion of searches and sorts. Good luck with it. I hope it's helpful, and we'll speak again.